Hi everyone, welcome back to Operations Research. So this is our third course. Again, we're talking about theory, and today we will talk about some theories about nonlinear programming. Mainly, we will focus on convex analysis. So first, we're going to talk about some motivating example, and then we will talk about the main details about convex analysis, and then we will try to solve single-variate NLPs, and then we will move to multivariate problems. So actually, we have learned NLP in the past, right? We know how to formulate some nonlinear problems. We also know that there are some algorithms that we may use to iteratively solve NLP problems, or somehow we should say find an optimal solution. But we actually have not discussed about how difficult it is, okay? So first, in general, in a nonlinear program, a local minimum is not always a global minimum. Let's very quickly take a look at this figure. So let's say we have a single dimensional problem. Our f of x is this guy, okay? So this is our objective function. The only decision variable x is a real number. So the feasible region is here, capital F. And very quickly, we may see that there is an optimal solution, x star, alright? So don't forget that when we say x star, it's actually here. It's just that because we want to make this figure easier to see, so we label x star around its objective value, alright? But x star actually means the x value. X star is optimal, or we should say x star is global minimum, alright? How about the other points? You may see that x1 is also a local minimum. Somehow that means around for all the points around x1, x1 is the lowest. Alright? So x1 is a local minimum, but it's not a global minimum. So for x4, it's somewhat similar. For x4, if we only focus on those nearby feasible points, then x4 is also a local minimum. So this actually creates a lot of difficulties for solving a general nonlinear program. Okay? If we are talking about linear programs, we know a local mean is always a global mean, something we mentioned in the past. But now for nonlinear programs, if we only find a local minimum, we have no way to tell whether it's a global minimum. Okay? So you may remember that your gradient descent, Newton's method, whatever, they typically go down, and then they stop when they find a point whose, for example, gradient is equal to 0. Okay, that's gradient descent. So if that's the case, gradient descent really can get you to a local minimum, but you have no way to tell whether it's global minimum or not. So a greedy search, something like gradient descent, may be trapped at a local minimum. Well, that's bad, alright? And also, in a nonlinear program which has an optimal solution, probably there is no extreme point optimal solution. So this is also something different from a linear program. If we are talking about a linear program, somehow we may focus only on extreme points. Because we know if there is an optimal solution, there must be an optimal solution at an extreme point. So for nonlinear program, this is not true. Just like this very simple example. So the feasible region is here. Your x1 and x2 are both non-negative, and their sum is greater than or equal to 4. We want to minimize x1 squared plus x2 squared. So the best thing we may do is to get to 0, 0. Alright? So 0, 0 is optimal. And very quickly from this figure, we can see that as long as you get closer to 0, 0, you actually optimize your objective value. So in this particular case, among your all feasible points, 2, 2 is optimal. So 2, 2 is optimal, and from the figure, you immediately see 2, 2 is not an extreme point. Somehow it lies at the boundary, but it's not an extreme point. Okay? The two extreme points are not optimal. So what does that mean? we cannot just focus on extreme points like what we did in linear programs. Somehow we have no necessary conditions that a global minimum must satisfy when we have some conditions or some constraints around us. All right? So this again creates or introduces you some kind of difficulties. We somehow in observation 1, we find that, well, we do need a necessary condition. We need the gradient to be 0 in some sense. Okay? But that's not sufficient. That's not sufficient. Or observation 2, we have no way to talk about extreme points or something that does not help at all. Okay? So overall, no one has invented an efficient algorithm that may solve a general nonlinear program, okay, to find a global optimum. That's just too difficult for the general nonlinear programs, all right? So what we want to do is that for a nonlinear program, we want to find some conditions such that a local minimum is always a global minimum. So that's one thing, one hope we want to have. Or also, we want to have some conditions that guarantees an extreme point optimal solution, guarantees the existence of this kind of situation. If we may have either one, then somehow it's easier for us to design an optimal solution, right? So we want to find some kind of problems, some kind of conditions to make this happen. So to answer these questions, that's something we will introduce to you. We will do convex analysis. We will define convex sets, convex and concave functions, and then define the so-called convex programs. Convex programs will tell you somehow we will have the first desired property, and a program that is very similar to convex programs will have the second property. We will see how this analysis may help us to make sure whether the algorithms find an optimal solution or not, or we may have better understanding about all those problems. That's about convex analysis.